different scales or units, right? All right. Okay. So that's that for the theoretical basis of dimensionality reduction, right? And I suppose I'll talk a bit about the step by step, right? Okay. Okay. So I want to talk about um, so in the in the implementation of the code, we have actually gone through the implementation without dimensionality reduction, which goes something like this. Like we train a data set. Oh, okay, so assuming like we've done data preprocessing, so we train the data set, right? So testing data set, validation data set. So we do cross validation as well, as previously explained, and then we have the test data set as well, and then we implement it and each binary classifier, right? So like we use cross validation as well. We use 20-fold cross validation, um, and then we try to visualize, right, the RC curves, and then we output the model compare the models in terms of its performance evaluation metrics, such as accuracy, precision, recall, F1 score, AURC, etc., etc., right? Okay, and then we do a comparison, right? But so like this is like raw data, right? This is using actually raw data, and so we're going to be actually looking at when we reduce the dimensionality, right? And in this case, we use the correlation coefficient, specifically Pearson correlation coefficient. So like we plot the heat map, we pick important features based on correlation coefficient, and then plot the heat map of important features, and then we split the data into training the testing data set. We implement the binary classifiers, and we implement cross-validation as well, obviously, and then we visualize, and then we do model comparison as well. So I suppose let's just jump into the code, right? Okay, so so the above right here is like where we were last time, and that's where we're gonna uh, continue. So here, what I'm trying to do is like I'm trying to like plot the heat map of like the raw data. So essentially using Seaborn right here, SNS. Um, and then this is actually the uh, the heat map, right? And then um, okay, so wait, please wait. Uh, okay, right? Okay, so one of the dataset's hallmarks is relatively high correlation coefficient scores. Only score no higher than zero point 0.6 will be considered acceptable, and correlation doesn't not mean necessarily mean causation, and that's why features will not be excluded only for their low correlation with diagnosis. Okay, so yeah, essentially we have actually done the heat mapping here, and then we essentially picked, right, the y, of course, the y value, the target value, the target variable would be diagnosis, and the x training features, right? These are what we picked essentially. So smoothness mean, radius, blah blah blah. All right, and then um, okay, so yeah, we pick like smoothness mean, radius, texture. Wait, I kind of forgot like what it refers to, and if correct me if I'm not mistaken, it is actually the wait. So um, if I'm not mistaken, if SE is standard error, I think. Yeah. Yeah. I think this is a standard error, right? Okay, so like we have the mean value and weak mean values of like 10 features, and then the standard error of 10 features, or like the worst or largest the mean of three largest values of these 10 features, right, essentially. And we pick smoothest mean, reduced standard error, texture error, smoothest error, smoothness standard error, symmetry standard error, fractal dimension standard error. Sorry, it's all standard error, not just error. And then texture worst. So like worst means the largest mean of the three largest values. Okay, right, and then symmetry worst, and then fractal dimension worst. So here we try to plot the correlations, right? And then we do a train test split, also maintaining the test size to be 0.34. And then yeah, essentially we just try to implement it, just like what we did last time, right? So like we try to find the fitting time, the scoring time, the accuracy, precision for call, F1, ROC, right? And then here we're just plotting the RC curve, right? And yeah, so this is what I do for each model. Like for like this is for logistic regression. I get all the values that I need for performance evaluation metrics, right? And then I plot the RC curve essentially. Okay, and then this is for decision tree. It's the same thing. The value is actually lower, so this is actually near perfect, like 0.99, and then this one is 0.90 or 0.91, I suppose, because it's point the numbers after that is like 0.6. And then we have SVM as well, we have LDA, we have QDA supposedly after this, right? And we have random forest, we have KNN, and then we have knife base, right? Okay, so essentially we get all the data right here, and yeah, um, these it's actually the same as last time, right? I chose the methods, right, like this. So let's just regression, decision tree, SVM, LDA, QDA, random forest, KNN, and naive base, right? And then I compiled like all the fitting time and the scoring time as well, and accuracy, precision recall, F1 score, AURC of all values, right, of all model. Um, So this is the columns, right, essentially, and I sorted by accuracy, and it's going to be descending because I set ascending here to false, right, essentially. So as you can see here, like you know, here, like for example, if we see the, let's say, the the recall, right, it goes down and it goes up, so like it's not sorted, but the only the accuracy here I think is sorted, and if there's like any other performance evaluation metric that is uh, sorted in a descending manner is actually like just by um, you know accident, yeah. So I think if it is represented this way, it is actually hard to perform like comparisons. So what I did was I make this, right, essentially like I'm trying to just have the accuracy and then get it sorted, right? So we can see like which one is the best performing according to like that specific performance evaluation method, essentially to yeah, okay. So okay, so it's actually the same thing. And then here I just did like yeah, the RC plot of like every single thing combined, and I actually thought like it's just like the first time I did it without, and the code without dimensionality reduction, because I thought like it's gonna have like some sort of insight, but turns out it's actually too jumbled up, so it's actually hard to see. But yeah, you can kind of see like, for example, like decision tree is actually pretty clear, and then like the pink one is knife base, I think it's pretty clear, right? So yeah, I suppose that's it for this video, and I'll see you in the next one.